All right, today we will finish up chapter 3. We're going to do a little bit more about bonding, and then we're going to do nomenclature. There'll be a few problems at the end, again from an old exam. Remember that since we have finished chapter 3, we will have a quiz. I believe the quiz is on Friday. On Friday, we will also have our first hour exam review. And then next Monday, we will have the exam. We're talking about ionic and molecular compounds. These are the ionics that we were talking about. This, if you recall, was an exception to the octet rule. That's sulfur tetrachloride. And I don't know if you caught it or not, but when I put this structure up, I said that it was referred to as a seesaw structure. Now it doesn't quite look like a seesaw. Well, now it's looking more like a seesaw. And now you can see chemists do have a sense of humor. This was an exception to the octet rule because sulfur, being in a third period, can accommodate more than 8 valence electrons. This one turned out to have 10. All right, quick review of what we talked about for ionic compounds. We said they contain a cation and an anion. Cation is positive. The compounds are held together electrostatically. So what happens is that chlorine or sodium donates an electron to chlorine. We wind up with the sodium cation, the chlorine anion. These simply attract each other. They do not have a defined geometry except when they're in the crystal. In solution, of course, they're simply separated solvated ions, and we'll see that later. Once again, if you look at the crystal structure here, this is a real crystal of sodium chloride. Nice, clean, perpendicular edges. And that's dictated by the fact that these guys pack in such a way that we have the sodiums in between the chlorines and stuff like that in what's known as a cubic array. All right, ionic compounds. We said that we could easily figure out the typical charge on at least the representative elements. That's the ones in these groups labeled 2 through 8. It's simply given by the group number, group 1, group 2, group 3, group 4. By the time we get over here, we're really not dealing with ionic compounds. Right here at 3 and 4 gets a little bit fuzzy, maybe 5 gets a little fuzzy. But when we get over here to 6 and 7, of course 8, we don't do compounds at all because those are the inert gases. But simply look at the group number, and that will give you a decent idea of the number of valence electrons. On this side, we're going to lose electrons. On this side, we're going to gain electrons. When you're building an ionic compound, there's something called the principle of charge balance. Now, charge balance simply means that the number of positive charges in the compound must equal the number of negative charges. If we had a compound and we were using magnesium and sulfur, well, magnesium is a group 2 metal, and as such, it will have a +2 charge. Sulfur is a group 6 nonmetal. It will pick up 2 electrons and give a -2 anion. If we wanted to make an ionic compound with these, we would simply need 1 magnesium, 1 sulfur, so our net charge is now 0. Same thing with something simple like sodium bromide. Sodium is group 1. It will lose 1 electron to give the sodium cation. Bromine is group 7. It will pick up 1 electron to give the bromine anion. And we need 1 sodium for every bromine. Again, our net charge is 0. If we're looking at sodium and sulfur, sodium, as we said, is going to form a cation with a +1 charge. Sulfur will form an anion with a -2 charge. That means in order to hit neutrality, we need 2 sodiums for every sulfur. Flipping it around, magnesium at +2, bromine at -1, we need 2 bromines for every magnesium. Not a difficult concept. When you're building these things, just remember you need to shoot for simple neutrality. Once we decide what our compound is going to be, we're going to write its formula using the simplest whole number ratio. Now this is for ionic compounds. There are exceptions to this rule. There are compounds that clearly exist as, say 2 and 2, but the default is always going to be to go to the simplest whole number ratio. So if we had a compound with magnesium and sulfur, we would simply write it as MgS. If we put Mg2S2, that's wrong. You want to go to the lowest whole number ratio. Sodium and bromine, NaBr. 2 sodiums, 1 sulfur. Once again, we're going to stick our 2 here as a subscript. So if we have 2 sodium cations for every sulfide dianion. And the same sort of thing here with magnesium and bromine. We're going to have 1 magnesium for every 2 bromines. Any questions? Nice simple way to put compounds together. Molecular compounds are a little more difficult. We name them differently, but for these, we're simply going to write the lowest whole number ratio. Now, I will make this slip over and over again, and I'm sure you will too, and everybody. When you're dealing with an ionic compound, you may not legally call it a molecule, because the molecule is reserved for a molecular compound. It's simply called a formula unit. Formula unit, like we said, is the lowest whole number ratio. NaCl, 1 sodium, 1 chlorine, HF, 1 hydrogen, 1 fluorine, 2 hydrogens, 1 oxygen, 2 potassiums, and 1 sulfate. Now remember, sulfate, we have 1 sulfur and 4 oxygens. These are all bonded together in a molecular complex. Now let's say we want to name a simple ionic compound. What you do is you're going to look at it. Remember, the ionic compound is going to have a metal and either a nonmetal or a polyatomic or something like that. Let's say we had magnesium and bromine. The first word of your name is simply going to be the name of the cation. It's presented as a separate word. So this is simply magnesium. Now the second word is going to be your anion. In order to get the name of the anion, what you do is you look at your element and you decide what the root of the name is. Now this is bromine. The root we're going to use here is brome. We're going to add the suffix IDE to the root. And this is therefore going to be magnesium bromide. Here's our root. Add IDE, magnesium bromide. Now note we do not use multipliers. Now that's good news and bad news. The good news is you don't have to worry about multipliers, do you? You simply look at this and say, oh, magnesium bromide. That's it. But if I gave it to you backwards, if I said draw the structure of magnesium bromide, well, you don't have a multiplier to tell you how many bromides, do you? So you have to look at it and say, all right, I can do this. It's always important. Magnesium is going to be +2. This is going to be -1. I need 2 -1s for every +2, and that's where we are. 1 sodium, 1 chlorine. Sodium is our first word. Our root is going to be chlor. And we're just going to add ide. K, of course, is potassium. This is sulfur. The root is going to be sulf. Our first word is just potassium. Our root is sulf, and we add ide. Be is beryllium. Again, the root for bromine is brome. So this is beryllium bromide. So the nomenclature here, going from the compound to the name, is really quite simple. Remember, you do not use multipliers, and the fact that you don't use multipliers makes this direction easy, but this one a little bit more complicated. Any questions? Well, let's just look at a couple quick problems. Look at my periodic table here and give me the formula for a compound that stayed with magnesium and chlorine. Well, step 1, we have to find them, right? Magnesium's here. Chlorine is a group 7, it's over here. Because this is group 2, this will be a group, or a +2 cation. Because we're over here at group 7, this will pick up 1 electron to get to argon, and that makes it -1. So we're dealing with a +2 and a -1. Now remember, we have our principle of charge balance. So for every +2, we need 2 -1s, and we can simply write it as MgCl2. Now if you named it, what would you call it? Magnesium chloride. All right, we have aluminum and oxygen. Aluminum lives over here in group 3, doesn't it? It will lose 3 electrons, therefore, and become a +3 cation. Oxygen is group 6. It will pick up 2 electrons, get over here to neon, and therefore it will be a -2. So we have aluminum at +3, and oxygen at -2. All right, in order to do charge balance, we need to find a ratio between aluminum and oxygen. It's going to give us a net 0 charge. Now this isn't rocket science. You can figure this out easily. Here's a little quick, cute dodge. What we're dealing with is aluminum +3 and oxygen -2, right? There's a little symmetry trick you can do. Let's just take and write aluminum and oxygen. And what we're going to do is, for our subscript here, that's how many aluminums, we just look at the charge on the oxygen. So this will come down to here. Whoops. This goes down to there, and this comes down to here. So basically, you just look at your charges, and they cross over. We must have 3 oxygens for every 2 aluminums.
So why does that become positive? Because it's going to aluminum? It's going to be positive?
Right, well, look, how many positive charges do we have now? Each one has 3, so we have a total of 6, right? We have 6 positives. How many negatives do we have? Each one is -2. We have 3 of them, and that's -6. So, you know, with a simple compound like aluminum and oxygen, it's not that difficult. There are some compounds that are trickier. And if you get something that's trickier, using a little crisscross is a nice dodge, a nice way around it.
So you could do the same thing with the first one?
Sure, you could do the same thing with the first one. We'll do one, yeah.
So every time there's like a positive and then a negative over here, or if there's just like anything, you just cross them and
Just
that's it?
cross them down and it works.
Okay.
It's a little symmetry trick. Beryllium and selenium. Well, we have to remember what they are, where they are. Beryllium is going to be Be. It's here in a group 2 metal, isn't it? Selenium is over here in group 6, hiding underneath sulfur. Because it's group 6, it will pick up 2 electrons and become a -2. Beryllium +2, selenium -2. Quite obviously, in order to hit charge neutrality, all we need is 1 of each. But just to prove that my method works, we can also just write it this way. Remember, we use the whole number ratio. So this winds up, even though it crosses down at 2 and 2, you simplify that to 1 and 1. That's what it looks like. Beryllium is actually an interesting metal. Very light metal, lighter than magnesium. It's used extensively in making nuclear weapons. For years and years and years, well, during when they did the first ones anyway, there were people that were trained to machine beryllium, a very good neutron reflector. So they machined it, you know, blah, 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 worked with it. Turns out that just like some of the heavy metals down here, beryllium has a high vapor pressure and is really quite toxic. So all these people that were bomb builders during the Second World War especially, essentially died of beryllium exposure. It's not something you want to keep a lump of in your cabinet as a souvenir. Any questions? Well, let's go ahead and take this list And just quickly on your paper, jot down acceptable names for each of these binary ionic compounds. What does binary mean? It just means we have two elements. On the first exam, you will be given compounds and you will be asked to write names. You will be given names and you will be asked to write compounds. All right, our first one here. 1 calcium and 2 bromines. We don't use multipliers. Our first word is going to be calcium. Our root is brome. This will be calcium bromide. Our next one, we have 2 aluminums. We have 3 oxygens. No multipliers, simply aluminum oxide. Lithium and sulfur. Our root here is sulf. We will call this lithium sulfide. 1 calcium, 1 oxygen. Calcium oxide. 1 nickel and 2 chlorines. Going to be nickel chloride. Now this last one we'll actually see is wrong. We'll understand why in just a few minutes, but this one should actually be nickel 2 chloride. But we'll do that in a moment. Let's go backwards. This is the one that's a little more difficult, isn't it? Need to look at the cation, decide the charge. Look at the anion, decide the charge. Get your lowest whole number ratio, so our charge is 0. Calcium nitride. Calcium is group 2, isn't it? That means it will be a +2 cation. Nitrogen is group 5. That means it will pick up 3 electrons and become a -3 anion. So we have +2 and -3. Using a crisscross, that means we would need 3 calciums for every 2 nitrogens. +2, -3, therefore 3 calciums, 2 nitrogens. Magnesium oxide. Magnesium, right there, is group 2. So that's going to be a +2 cation. Oxygen is over here. It is a group 6. Therefore, it will pick up 2 electrons. It will be a -2 anion. We have +2, -2. If we crisscross, that would still be 2 to 2. Simplify that, 1 to 1. Lithium is a group 1 metal. It will form a +1 cation. Iodine is a halogen. That's group 7. Therefore, right over there, therefore, it will pick up 1 electron, -1. This is simply Lil. Lithium iodide. Barium phosphide, barium. Group 2 metal, +2. Phosphorus, where's phosphorus? Right there under nitrogen. It's a group 5, isn't it? Therefore, it's going to pick up 3 electrons. So we have +2, -3. Do our crisscross, 3 bariums for every 2 phosphorus. Yeah.
Can we use a periodic table, like when we bring one in for our quiz and our test?
Oh yeah, everybody will have a periodic table. Remember, one of the great things that we try to do is to reduce test anxiety, so I'll keep telling you the important things. You will have a periodic table. Yes, you will. Number 2, remember you also will have your 3x5 card. That's 3 by 5 inches, not 3 feet by 5 feet, okay? So you'll have your 3x5 card. So, and you can write whatever you want on that. So if a concept or memorizing something is giving you a little bit of a problem, you don't relax, you've got this, it's a nice memory aid. Beryllium fluoride, beryllium Be, that's a group 2. Fluorine, halogen, that's going to be a -1. You're going to need 2 fluorines for every beryllium. And that's what it looks like. Any questions? Yeah.
For lithium iodide, why isn't it Li3I? Because
Iodine is group 7. So it's going to pick up 1 electron,
Oh.
right?
I flipped it backwards. Yeah, I got it.
All right, well, you know, these are the ones that are really easy to remember. But remember these guys, the ones that made everybody shudder? The polyatomics. We will also make and name compounds that are ionic that have polyatomic anions. The name here is really simple, just like before. We will use the cation. We will then simply put in the name of the polyatomic ion. You must, however, remember the charges on these guys so that you can do your crisscross thing and make it work. All right, CO3, what was that? It's the parent compound. So it's an 8, isn't it? We're looking at carbon, so we're going to call it carbonate. Calcium is our cation. Don't use multipliers. Therefore, this is simply calcium carbonate. Calcium carbonate, that's marble. Also chalk. Very, very common element or compound. 1 calcium, 1 carbonate. Now in our next compound here, NH4 is our one and only cationic polyatomic. Remember? The only positively charged polyatomic that we're going to do in all of 110. That is, NH3 would be ammonia, so this is ammonium. Our anion here is chlorine, so it's going to be chloride. The charge on ammonium is +1. This is simply ammonium chloride. SO4, who remembers what that is? It's our parent. So it's an 8, right? And it's got a sulfur in it. So it must be sulfate. Na is sodium. This is sulfate. No multipliers, so it's simply sodium sulfate. Now, if this is sulfate, and we take one oxygen off, what do we get? Sulfite, right. The charge stays the same. This is -2. This is also -2. We have lithium and a sulfite. It is simply lithium sulfite. Now, PO4, that's the parent for phosphorus. That's phosphate. PO4 is phosphate. It's a -3 charge. Here we've stuck a hydrogen onto it. So when we name this, what do we call it? Simply hydrogen phosphate. If phosphate is -3, adding a hydrogen consumes one of the negative charges, so this is -2. K is potassium, therefore we have a 3-word name, all separate words, potassium, hydrogen, phosphate. Now, just like the other example, because we don't have multipliers going backwards, you not only have to remember the carbonate is CO3, but you have to be able to figure out the charge thing. So let's look at these. Potassium is no problem now. See how simple these things get when you do them for a bit. We know potassium is going to be +1. What the heck is permanganate? That was on our last set. It was kind of a special case, the only manganese that we're dealing with. And it's MnO4. Manganate, MnO4, and it's -1. So we have one potassium at +1, one permanganate at -1, KMnO4. Now when you think about polyatomics, remember, all of these oxygens are attached to the magnesium. They're all covalent. It's a lump, it's a little ball that you pair up with the potassium. We just did sulfite. If sulfate is SO4, sulfite is SO3. If sulfate is -2, sulfite is also -2. Therefore, 1 barium at +2, 1 sulfite at -2. Aluminum chlorate. It's 8, it's a chlor, so we know it's the parent, right? Chlorates. Chlorate, perchlorate, chlorite, hypochlorite, all are going to be -1. Chlorate is going to be ClO3, -1. Aluminum, group 3, is going to be a +3 cation. So to hit neutrality, what do we need? For every 1 aluminum, we need 3 of these negatives, don't we? Now think about how you're going to write this. It's ClO3, and we need 3 of them. What you're going to do is take the entire polyatomic ion, put it in parenthesis, and then show that we have 3 chlorates per aluminum. Silver nitrate. We did nitrate as a Lewis structure. We remember that that's NO3, and it has a -1 charge. Silver, I haven't talked too much about silver. Silver is virtually always a +1. It's a transition metal, but whenever you see silver, it's +1. So nitrate is -1, silver is +1. What's the symbol for silver? Ag. And finally, remember cyanide. Whoops, remember cyanide. Cyanide is Cn-. There's a triple bond between the carbon and the nitrogen. Looks a lot like carbon monoxide that we did, except it has a negative charge. Barium is +2. So we need 2 cyanides for every barium. Write it. This one's important. Make sure you write this right. We have to make sure we convey that we have 2 cyanides for every barium. Therefore, we're going to put cyanide in parenthesis, like we did here, with a subscript of 2. If you had written, left out the parenthesis and put Cn2, that would sound like you had carbon with 2 nitrogens, right? Can't do that. You need 2 cyanides. Always remember to put your polyatomic in parenthesis, and then put your subscript to show how many you need. Well, this takes a little bit of practice, not a whole lot. Got some things to remember, but we can all do that. Let's just very quickly look at some more. And let's name these guys. Well, Pb is what? Lead. O is oxygen. So this is oxide, right? So we would call this lead oxide. Now, remember we don't use multipliers, do we? No. So, what's this next one called? Well, that's lead. That's oxygen. That's lead oxide 2. This is iron. That's oxygen, right? So this is iron oxide. And so is that. And so is that. Clearly, we have a problem. Don't we? We need some way to explain in our name that we have 2 oxygens, 2 irons, 3 oxygens, 1 and 1, etc. But we can't use the multipliers. These compounds differ in what's referred to as their oxidation number. Their oxidation number is simply a fancy word for their charge. We know that oxide is going to be a -2, right? Therefore, lead, in order for this to be neutral, must be +2. That makes sense, right? Here, how many negatives do we have? Each oxygen is -2, right? So there are 4 negatives. This must be a +4. This iron must be a +2. This one must be +3. This one must be +2. The oxidation number. We will get to the oxidation number in chapter 5 when we do what are called redox reactions. In redox reactions, oxidation numbers change. Very important class of reactions. Basically, all it does is it tells us how many more or fewer electrons an element has in your compound relative to the stuff as it sits in the periodic table, relative to the pure, simple element. If it has 2 fewer electrons, here's our lead. Lead is going to have, I don't know, some number of electrons to be neutral. If it loses 2 of them to become a +2, we would simply say its oxidation number is 2. If oxygen gains 2 electrons, its oxidation number would be -2. Simply compare the element in the standard state, the periodic table, with the element in your compound. So, we're simply going to look at the charge on the cation. The oxidation number we can do for both the cation and the anion. The charge on magnesium is going to be +2, isn't it? Therefore, we could say its oxidation number is going to be +2. Bromine is a -1 anion. Therefore, its oxidation number is +2. Oxidation number of bromine is -1. Simply the charge. Fancy word for the charge. For lithium phosphide, lithium is a +1 ion. Phosphorus is a -3 anion. So if I asked you what the oxidation numbers were, you would say +1 and -3. All right, so how do we incorporate this into a name? Actually, let's look at our full list of rules here. We don't need to know these until chapter 5. Since we're comparing elements in their standard state, if we have a pure element, it's always 0. As we've seen, group 1 metals form +1 cations, so that's +1. Group 2s, +2. Chlorine is -1. These get a little more complicated. Again, we'll deal with those in chapter 5. But there's a set of rules for it. Right now, all we care about are the charges. Again, chapter 5. So let's look at our compound here. We know our oxygen is going to be group 6. It's going to pick up 2 electrons and become a -2. That means the oxidation number, in order to be neutral, oxidation number of lead must be +2. Once again, our oxygen is going to be a -2. That gives us 4 negatives. That means the charge, or the oxidation number of the lead, must be +4. So what you do really is you look and see what you can rely on. Oxygen, halogens, things like that. Halogens are going to be -1. Oxygen, sulfur, whatever, is going to be -2. Use that, and then work on the charge of your cation. So look at these guys. What's the oxidation number for the iron in iron sulfate? What's the charge of sulfate? -2. If this is neutral, the iron must be +2. Oxygen will form what kind of an anion? A -2, right? So we have 6 negatives, don't we? That means we must have 6 positives. If we have 6 positives and only 2 irons, each iron must be +3.
How did you get the 6? I'm so confused. How did you get to the 6? How? Because.
Okay, how did we get to 6? Every oxygen is going to be a -2, isn't it?
Okay.
We have 3 of them.
Okay.
3 times -2 is -6. So we need
So you
6
look-
positives.
So you look at this, where is the allocation of it, and then kind of multiply by the number, how many you have.
Right. Oxygen is going to be group 6, isn't it?
Yeah. So that's,
Therefore, it's going to pick up 2 electrons and be a -2.
and then times how many times?
Times how many of them, right. That gives you your total number of charges. All right, how do we put this in a name? Well, we're going to use Roman numerals. Now, don't worry, you don't need to know what 50 and 100 is and stuff like that. All we're going to do is figure out what the charge or oxidation number is. We're going to stick it immediately after our cation, uppercase, in parenthesis, in Roman numerals. Every oxygen is a -2. We have 2 of them, right? So that's how many negatives? That's 4 negatives. Therefore, our lead must be +4. We will therefore call this lead 4 oxide. Oxygen is going to be -2. We have 1 lead. That lead must be +2, right? So we show that as lead 2 oxide. Carbonate is a -2 anion. Therefore, iron must be +2. So we call this iron 2 carbonate. Bromine, halogen, group 7, -1. We have 3 of them. That's 3 negatives. That means our iron here must be +3, and this is iron 3 bromide. Any questions? Now you'll note that there is no space in between the cation and the charge. If you're writing it on an exam or something, I don't care if it looks like there's a space or not. Frankly, nobody cares. But on Blackboard and on the tutorials, it matters. So don't put the space in, it doesn't work. Speaking of tutorial, my gosh, take this compound and write the name. Well, BA is barium, isn't it? Where is barium on the periodic table? Second group. Right there, I think. Or somewhere. I can't see very well, but it's over there somewhere. Because it's a group 2 element, it is always +2. If something is always the same charge, you don't have to put in the Roman numerals. So all we have to do here is write barium. This is iodine, therefore this is barium iodide. Copper is a transition metal. If it's a transition metal, you're going to have to put the oxidation number in, because they can be all over the place. Iodine is group 7, isn't it? So what kind of an anion is that? That's a -1. Therefore, the copper must be +1. And how do we write this? Copper, 1 iodide. On this tutorial, it will actually tell you if your first part or second part is wrong, so you can go and try again. Kind of cute, actually. Now this isn't chloride, is it? Chloride is ClO3. This is bleach. This is hypochlorite. Hypochlorite. Just like chlorate is -1, hypochlorite is also -1. If we have 3 negatives, we must have 3 positives. Iron is a transition metal. Therefore, we have to show the charge. Therefore, this will be iron 3 hypochlorite. Bless you. Now, as I always say, these tutorials are really important. The questions on Blackboard will come directly from these tutorials. Remember, we have quiz 1, 20-pointer. We're taking. There will be questions exactly like this on that quiz. Please practice these. All right. We did ionics. Let's do molecular. Remember, molecular compounds have covalent bonds, don't they? Ionic compounds must contain a metal or ammonium. Molecular compounds must contain only nonmetals and semimetals. So if you look at a compound and you decide it's molecular, we're going to name it essentially the same with the one real difference, that here we will use multipliers. Multipliers are easy. Mono, di, tri, tetra, penta, hex, hept, oct, non, dec. Really, the first, these guys are the ones that we'll see. But we all kind of know those. Just like before, we're going to name our first element in the compound. Just name the element. We're going to look to see what's next. Take the root and add IDE. Only difference is we will now use multipliers. There is one exception. Mono is not used for the first element. If you only have one of the first element, do not use mono. If you only have one of the second element, then you use mono. It's trivial. Let's say we have CCl4. They are both nonmetals, aren't they? So we say to ourselves, okay, molecular compound, I'm going to use multipliers. My first word here is just going to be the name of the first element. And that's going to be carbon. We don't use mono. Not for the first element. Now, our next one is chlorine. That's going to be a chloride, isn't it? But we have 4 of them. What's our multiplier for 4? Tetra. Therefore, this is carbon tetrachloride. Tetrachloride, all one word. Now just think how simple this is to go backwards. If I tell you draw the structure of carbon tetrachloride, all you have to do is put 1 carbon and 4 chlorines. SO2. Step one, they're both group 6. They're both nonmetals. So yes, it is a molecular compound. Our first word is just going to be our sulfur, isn't it? We don't use mono. This is going to be oxygen. It's going to be oxide. And we have 2 of them. What's our multiplier for 2? It's di. Sulfur dioxide. N2O. Our first word is going to be nitrogen, isn't it? But we have 2 of them. We have to say that. How do we say 2? Di. So this is simply di-nitrogen. Now our next element is oxygen. That's going to be an oxide, right? But there's only 1 of them. Therefore, this is monoxide. Now, the multiplier for 1 is actually mono, isn't it? But if I wrote monoxide, I would have 2 O's in a row. And that just looks wrong. Looks funny. So we don't put them in there. Go ahead and write this one. We have 2 nitrogens, therefore our first word is dinitrogen. We have 5 oxygens. 5 is a pent, isn't it? So we're going to have pentoxide. You'll also know that penta is what's actually on the table. And so pentaoxide, again, that just sounds stupid. So we get rid of that and just do pentoxide. Now on an exam or something, if I asked you to name something like this, and you happen to put the AO in, would I be upset? Would I really care? No. I really wouldn't care. Because the most important thing about nomenclature is that you're unambiguous. If the name you write clearly, concisely describes the molecule, that's the main point of it. Now there are rules to follow, yeah. So if it would work a lot, you might lose a little bit, I don't know. But you might not. It all depends on how you screw up. If you do a tutorial or Blackboard and you kind of leave this out, I've tried to fix Blackboard so it will take it even if you screw it up. Sometimes that works, sometimes it doesn't. But try to remember when you have 2 vowels in a row, pretty much get rid of one of them. All right, quickly, let's name these guys. I will hush for a moment while you do this. Our first compound here has 1 carbon, 2 oxygens. Both of those are nonmetals. It's molecular. Our first word will simply be carbon, no mono. We have 2 oxygens, so it will be carbon dioxide. Our second element here, our second compound, we have 2 hydrogens, 1 sulfur. Hydrogen is still a nonmetal here, so is sulfur. It is molecular. We must use di. So we will call this dihydrogen monosulfide. Now here you see I stuck the O in because we didn't have 2 vowels in a row. Silicon is a semi-metal. It's green. We have 4 hydrogens. We don't use mono. So our first word is simply silicon. We say 4 using tetra, don't we? Silicon, tetrahydride. 3 is tri. We're going to have a trioxide. S is sulfur. This is simply sulfur trioxide. Once again, 3 chlorines, that's a tri. It'll be a trichloride. This is nitrogen. Again, they're both nonmetals. Nitrogen trichloride. Let's do it backwards. You remember tetra is 4, right? What's 6? Hex. Therefore, we have 4 P's. Is that potassium? Of course not. Phosphorus. So it's going to be a tetraphosphorus hexasulfide. See how simple that is? 2 iodines. Diiodine, 2 iodines. And what is 7? Hept. Hept, right. Now, it's going to be a heptaoxide, so we're going to have to get rid of one of the vowels. We'll call this diiodine heptoxide. One oxygen, 2 fluorines. Don't use mono. So it's oxygen. 2 is difluoride. 1 carbon, 4 hydrogens. 4 is tetra, right? So this would be carbon, tetrahydride. But if you called it that, nobody would ever know what you're talking about. This is the organic compound. Methane, natural gas. We've seen that before, CH4. Organic chemists have their own way of naming carbon compounds. Finally, 4 sulfurs, 2 nitrogens. Tetra, sulfur, dinitride. Quickly, just write the formulas. This is trivial. This is so simple. because all the information is right in front of you, and you can do this as fast as you can write. We have 1 nitrogen, we have 3 iodines. We have 2 phosphorus, 5 oxygens, 1 sulfur, 3 chlorines, 1 nitrogen, 1 oxygen, 1 hydrogen, 1 chlorine. This last one is HCl. This is actually hydrochloric acid. We'll see when we get to chapter 8 that there are special rules for naming acids. But right now, hydrogen monochloride works fine. Any questions? All right, well, let's just do a quick reality check here to finish up the chapter. We have talked about molecular and ionic compounds, right? We said that in a molecular compound, like CO2, we share electrons. In an ionic compound, we transfer the electron totally from one element to the other. These actually represent limits, however, of real bonding. Whenever you have the same 2 elements in a covalent bond like this, so CO2, H2, all those guys, we have perfect sharing. Yes, we do. But if we have a covalent bond between different elements, we'll see that the sharing is far from perfect. That in fact, as we change the elements, the bond between them begins to resemble more and more the ionic bond in something like sodium chloride. Now, we're not going to talk a lot about this, but I just want you to understand the basic notions here. Let's look at 2 molecules, hydrogen and hydrogen fluoride. These are both molecular compounds. They both have covalent bonds. Okay? We can take H2 and we can calculate what's known as an electrostatic potential map for the molecule H2. What the electrostatic potential map does is it calculates essentially the electron distribution in the molecule. This is real useful. We'll see that. But okay, so that's what electrostatic potential map does. It's a computer calculation, and then we use color to represent the distribution, positive, negative, whatever. If we do this for hydrogen, we feed this into our computer, it generates a region of space where the electrons are likely to be, something like that. And then it goes and it colors it, depending upon the electron density. For hydrogen, you wind up with something that looks like kind of a little egg. It's green. Green all over. We have nice, uniform electron density. Both elements are the same. Sharing is perfect. Now let's look at hydrogen fluoride. Do the same exercise. We will calculate a region of space where you're going to find electrons. And then we're going to color it. When we do this, we wind up with a nice colorful Easter egg. Now we've set our computer so that wherever there is lots of electrons, we're going to show that as red. Wherever electrons are missing, we're going to show that as blue. What this basically says is fluorine is hogging all the electrons, isn't it? It's not sharing very nicely. We have positive charge at this end of the molecule and negative charge at this end. We'll see that this is very, very important when it comes to acids and bases, things like hydrogen bonding, etc. This is what's known as a dipole. We show a dipole in a molecule with an arrow that's crossed on one end. This is the positive end of the molecule, or the covalent bond, and this is the negative end. Now you don't have to draw it with a nice gradient. Typically you just draw it as a line, cross it, arrow on one end, cross it on the positive end of your bond. Now why is this? How can fluorine get away with hogging all the electrons? That's not nice, is it? Something called electronegativity. We're looking here at hydrogen and fluorine. This is our periodic table with another number put on there. You don't need to remember any of these numbers. Okay, you don't need to remember anything. That makes you happy. I know. We need to remember some things, but not the numbers. This is a relative scale. Okay? It goes from 0, supposedly, up to about 4. If you look at the periodic table, the smallest numbers are down in this corner, the largest are up here. As you go across, they get bigger. As you go up, they get bigger. Therefore, carbon is more than silicon. Nitrogen is more than phosphorus. Oxygen more than sulfur, etc. Electronegativity is a simple property of an element that describes how strongly it attracts electrons to itself. Fluorine, the most electronegative element in a covalent bond, will draw the electrons towards itself. That's where the thing comes from. Now, why is this important? Because this generates what we'll call a polar covalent bond. You'll see that polar covalent bonds are actually the origin of chemical reactivity. So this is the kind of a why. Why do things react? Polar covalent bonds are a big part of that. Now we're going to return to electronegativity. We're going to return to polar bonds, dipoles, and stuff like that when we start talking about water in a later chapter. But this is, I want to make the point here that covalent bonds are not always shared equally. That in fact, we do have high polarization in many of these bonds. All right, let's wind up just by quickly reviewing some simple nomenclature. Take these guys and write names. CS is cesium, isn't it? Cesium's a metal. Therefore, this is ionic. No multipliers. SO4 is sulfate. This is cesium sulfate. Magnesium is a group 2 metal. It will form a +2 ion. Cn is cyanide, -1. We have 2 of them, but no multipliers. Simply magnesium cyanide. NO3, we'll never forget NO3. We did it in class. That's nitrate. K is potassium. The parent for the phosphorus oxyanions is phosphate, PO4. If we're missing one oxygen, what is it? Phosphite. Therefore, this is simply calcium phosphite. SO4 is sulfate. SO3 is therefore sulfite. We have a hydrogen, so this is sodium hydrogen sulfite. One more set backwards. Draw me a compound using sodium and sulfate, barium and chromate. Chromate is CrO4. Aluminum and carbonate, magnesium and dihydrogen phosphate, beryllium and hydroxide. Chromate is one we didn't talk much about. Again, it's CrO4 with a single negative charge. Sodium is +1. Sulfate is -2. We need 2 sodiums. Barium is +2. Chromate is -1. Oops. Guess it's -2. Sorry. Told you it's not one we use often. Therefore, this is simply VaCrO4. Aluminum, group 3 metal, we know this is going to be +1. Carbonate is going to be -2. So we have a +3 and a -2. We could just do crisscross, can't we? Going to need 2 aluminums, 3 carbonates, magnesium is +2. Now if phosphate is -3, and we add 2 hydrogens, that drops it down to -1, right? Every hydrogen drops it 1 positive charge. So we start at -3. This takes it down to -1. Magnesium is a +2. Therefore, we need 2 of these guys for every one of these. Finally, when we do acids and bases, hydroxide, remember, water is going to form hydronium and hydroxide. This is OH minus, beryllium, group 2 metal. We need 2 hydroxides for every beryllium, and it looks like that. We have time for one or two old test questions. Real test question number 1. In the Lewis structure for xenon oxytetrafluoride, which you don't have to name, how many electrons are around the xenon? Well, there are two things that should go through your mind. First is, oh my goodness. And the second is, wait, that's an inert gas. I didn't know it made compounds. Well, it does. You have to like sit on it to make it do it, but it does. How are we going to do this? Well, let's just do it by drawing a Lewis structure, okay? That's the simplest way. Xenon, 8 valence electrons. We have an oxygen, and we have 4 fluorines. Let's just stick them around somewhere. Put our oxygen. Now, let's try to figure out what we're going to do. Well, this guy's no problem, is it? Make a bond there, no problem. Now, I've shown this as a pair of electrons, but remember, that's just bookkeeping, isn't it? So I could take one electron, bond it to here, one, bond it to here, and that's good. Here we have more of a problem. We have 3 electrons in both bonds. So let's just get rid of a couple by putting them in storage. And now suddenly it looks very simple. So let's draw our bonds in. Can't forget we've got this guy sitting out here, so let's put it back. And now let's count. We have 2, 4, 6, 8, 10, 12. Here we have an anion, sulfur 2 minus. How many protons are in there? Where is sulfur? Right here under oxygen. What's its atomic number? 16. Doesn't matter how many electrons you have, does it? Only the fact that it's sulfur, its atomic number is 16. We don't care what its mass number is, but typically it's 32. Therefore, regardless of how many electrons you have, it is still only 16 protons. The number of protons determine what the element is. Chlorine. We actually did this in class, didn't we? This exact question. And it still showed up on the exam. And everybody, of course, got it right. Group 7, we have 3 at group 6. Have to add 1 electron on the chlorine. All we do now is simply draw our bonds. and that is chlorate anion. One more quick one. Name, real test question, name following molecular substances. One nitrogen, one oxygen. Nitrogen monoxide. One silicon, four chlorines. Silicon tetrachloride. Two phosphorus, diphosphorus, pent oxide. One carbon, two oxygens, carbon dioxide. All right, I will email everybody a thing. Well, maybe I won't mail it to you. I will put it on Blackboard, okay? So you can print mini prints for the exam review on Friday. The lab thingy for the first lab is up. Simply fill it out, click submit. If you change something, do it again. You can do it over and over again. On Wednesday, our lab is this very simple little measurement lab. Only thing you need to be aware of is the significant figures you use in your measurements. Okay? So review the significant figures before Wednesday. Have a great day.